Alright, so what we're doing, as I was saying, is just doing this problem right here. We're going to set up the loops for kinematic analysis. And this right here is supposed to say link typo. So anyway, so essentially what we're going to do for this one is we're going to do the same thing we have been doing, which is creating the vector loops, right? And once we create the vector loops, we're going to get the vector equations and the scalar equations, and then any additional equations we need to solve the question, right? Because there might be one in here that we might have 5 unknowns and 4 equations, right? And as you can see, there's no rolling contact in this question. Pretty straightforward. So that means if we have to find an additional equation, it will be it'll be some angle, right, or some length. You see what I'm saying? So, all right. So right here, we're going to start. So the first step, right? The first step to this question, which I'm going to put in a text box. I actually have a text tool on this one, so we're moving up in the world. So step 1 was to create the vector loop, maybe vector loops for your question. But in this question, as you can see, there's a hint that says 2 vector loops are required. So create the vector loops for the mechanism. Right? So, step 1, we're going to create the vector loops. So, let's, I'm going to get the line tool out. So, now that we have the line tool, who wants to start with the first vector loop? Now, this one is pretty straightforward, right? There's kind of you can kind of already see where we might go with this at the beginning, like the start of our vector loops, just because it's it's kind of like a problem of 2 halves, right? You know, we have this whole type of thing, and we have this thing in the middle. So we're gonna start at link 1 though, or link 1 to 2, like we always do, right? So can someone tell me where they might put the first link, the input, or the first line, the first vector, the input, which is 2, right? Anybody want? Is it? Tell me if I'm wrong. Does that look good to you guys? I got a thumbs up from the class, so it is. Looks good. So this right here will be R2, right? Although that is a really big R2, so we're gonna turn that down a notch. So R2 is right there, right? So I think everyone's pretty comfortable with that, right? Essentially, if you have a revolute link, which is what this is, essentially you have a revolute joint here, but this is a slider, but it's pinned on the other side, right? So essentially it's the same thing as the revolute link, right? So you just draw from one end to the other. No harm, no foul there. Now, how do we think we should do the next one? So remember, this is a slider. So what do we do with sliders? Jackson has answered this question every time, and I have a feeling he'll do it again. So Jackson, what do we do with sliders? Up the channel. He's correct. So what he is saying is that we should go up here, right? Up to the ground. Okay. Cool. I agree with that one. What would you call this one? It's not really a trick question. Like, you can call it whatever you want, really, but R3. I like that. So we're going to call it R3. So I'm going to put an R3 right there. So we have R2, R3 so far. Now remember, this question says it requires 2 vector loops. So we have an option here, right? And like I said, I'm trying to talk you guys through it, so whenever you see something like this, you don't get too caught up. So we have 2 options here, right? So what we could do here is we could continue along this, right? Pretty clearly, we could continue along. Or what is the other option, Jackson? Or anyone, Sean, Salem, Rosendo, whoever wants to answer. What is the next option? What is the other option that we could do? Because the point of making 2 vector loops here is to try our best to simplify the loops as much as possible. right? Because if we did this in one, it would be really convoluted, and I honestly don't think you could do it. Because it would like go back in on itself, and it'd be really weird. So, what do you think we could do here that would make this as simple as possible? Specifically, this loop right here. Go back to down to the ground, correct. So, and you're going to call that what? It doesn't really matter, but call it something, right? You can make it R31, R whatever. It doesn't, just give me something, and whatever the solution manual has, I'll just like draw a little key over here that says what they have in, with basically in difference to us. So I'm going to call this one, we'll call this one R31. How about that? Alright, so we have an R31. So we went from 2 to R3 to R31. I like that. That is a good loop. And we are going to call this loop, let me change the color here. Actually, we're going to keep it black. We're going to call this loop Loop A. So this is Loop A, the first loop. So I'm going to write this out over here with obviously bigger text. Loop A. It is R2 plus R3 minus R31. Once again, remember, these are just sort of arbitrary. We're not really worried about that. But I don't want to draw arrows on here because arrows would kind of make this really messy. I like where it's at right now. I'd have to draw arrows and, could be bad. So, loop A is very simply just that, right? Would you guys agree that all good there? So, now we have to do loop B, which I shouldn't have put a text box yet. So, loop B, which is what's coming after, loop B. So how do you think we should start loop B? Now remember, the loops, for them to make sense in our terms, they have to start at the same place and come back to that place. And so remember, we should have it start at the same place as back here. Because remember, all these loops are with respect to the input link. So the input link must be in the loop, right? You see what I'm saying? It must be in the loop. So the input for here is, let me change the color if I can, actually. I don't know if you can change the color. Anyway, nope, can't. Anyway. Oh, there it is. You're right. Anyway, so what about the next part? So I think we can all agree that we need to start at the same link, R2, right? Does everybody agree with that? Because if we don't start there, our equation, our vector loop, is not going to be in terms of the input, right? Which is what we want. Yes, so ground to ground is correct. I agree with that. So right here. And there's a reason I saved this one. I saved R1 because this is where I knew it was coming at. So I like that. R1. I like that. Now what do you think the next one should be? I mean, this one is fairly straightforward as well. Up the channel. So up this right here. Oh, that is not what we were looking for. We salvaged it. Look at that. So that's right here, R4. I think you guys would agree naming it R4 seems to make sense. And you say down to ground 1. I would not go down to ground 1. And the reason why I wouldn't do that is because, do you see this little gap here? Our vector loop right here does not take into account how this thing moves and how it gets different from here. So think about it this way. If we slid R3, or if we slid 3 all the way like down this way, that means that this part is now gotten further apart from here, right? So we have failed to get that motion in our equation, right? So with that in mind, what would be your option there? Let me get the line tool out. You guys think, oh man, why is it doing that? No. Stop that. Do you guys think that that makes sense? What would I call this one? R4 something? We'll call it that. I'll just call it R41 or something. R41. So, do you guys believe that that makes sense? And remember though, the loop has been completed. And the reason why it has been completed is because we already know all this, right, from our first loop, so it can still be contained. And so we could go R2, R3, R41, R4, R1, and back, right? It's been contained. We're good there, right? So, really quickly, is this good for everybody so far before I like move on any further? Okay, so the reason why, if you did one loop here, Jackson, which maybe at the end I will show you, but essentially if you did one vector loop, you would have to do this. So think about it this way. You would go up, down, or up to here, to here, to here, to here, and so you're saying why can't we just do this whole outside part, right, and not this middle part? Is that sort of your question? So essentially what ends up happening is that some of these, and I don't know if this one turns out to be like that, but if you don't structure the loops like this one, you end up with a lot of unknowns and only 4 equations. So for example, I know specifically that there were questions that whenever I was in the class that I didn't set the vector loop up like, I remember doing this question as a matter of fact. I remember setting the vector loop up a different way, and I ended up, whenever I tried to do it, I ended up with like 6 or 7 unknowns and 4 equations, which means that those other 3 equations had to be found from like angles and geometry in here. And the problem with that is though, is like I said, you can probably do it with one. I don't disagree with you there. You could probably do it. Like it says 2 vector loops are required. I don't know if they're required. But the reason why I would caution against not doing it in 2 is because at the end of it, you might realize that you have so many unknowns that you can't possibly do extra equations on here without creating more unknowns. Because remember, the reason why those angle changes, like those 90-degree angle changes, are really good is because they don't create extra unknowns, right? Because you know it's just a pi over 2 away. But if you create another unknown of something that changes and try to relate it back, you've added an unknown, but you've gained an equation, which means you haven't actually made any headway, right? You've stayed the exact same. And so, like I said, you need to set up the vector loops in the simplest possible way. And would you guys agree that this is fairly simple, right? We have a triangle here, and we have this outside part. Although I don't know if that's the exact way that they have it set up, but yeah. So what their solution is that, and the one that happens to be right, is that they do this. So let me Like I said, not necessarily right. How about right is not the word. The easiest way that I can see to do it is doing this and doing this. And like I said, Jackson, at the end, if we have time, I will try and do it in one, and I'll show you why you might not want to, and why it would be maybe harder. But anyway, so right here we have our 2 loops, right? But I agree with you. I think that most of them can be done in one. The problem is that do you want to? That's always the question. Do you actually want to do it in one? And a lot of times the answer is no. So we have R31 plus R41 minus R4 and minus R1. Equals 0. So what we did for the second loop is we went here, to here, to here, and to here, right? So these are our 2 loops. That is the first part of the question. And like I said, for you guys, you won't have to do this on the exam. I'm going to provide, and on your homework, I think I provided you the vector loop, right? Because I'm not testing you over that anymore. I'm testing you over whether you can identify the knowns and unknowns and do the equations right, the derivatives right. But you know, for us, this is what we're talking about right now. Yes, it will be the same for the exam. I'm not going to have you make a vector loop because it would seem unfair to me that, let's say, like the vector loop 1 went really badly, right? Like let's say you did like 60 or 50 or something. And then on the next exam, you get a 60 or 50, not because you don't know how to do derivatives, because you couldn't do the vector loop again. Basically, I'd be punishing you for the same subject twice, rather than testing you on the new subject. See what I'm saying? Doesn't quite make sense to me if I do it that way. So, we will not be doing it that way. Velociraptor say hell no. So, not in this house. Alright, so, next one. Step 2 was to identify the knowns and unknowns. So, knowns and unknowns. So, we do the exact same thing that we did before, except we are going to do it by loop this time. So, loop A. What are the knowns and unknowns for loop A? So, let's do K and U. So let's start with the knowns, right? Because that's always the easiest one. I think you guys would agree. The knowns is fairly easy. What would you say is the knowns for this one? Let's start with R2. I think that is correct. R2 is known. What about theta 2? I don't have a theta, so I'm just going to have to write theta 2 like that. All right. Anything else? Uh, 3-1, is that... What about... You're talking about this one? R3? Oh, no. Oh, you're talking about ground to ground. Are you talking about the angle and the length? Because you are correct. R3-1. I forgot we were doing knowns at this point. So yes, you are right. And the reason is because this is to ground, therefore this angle will never change, right? Because these are two grounded parts. A lot of people make the mistake and they like see this part moving and they think that this goes with it, but it doesn't. They're just ground to ground, and so it doesn't affect it. So here to here, that length never changes, that angle never changes. So that is our list of unknowns. So by process of elimination, what is now unknown? We have R3 and theta 3. Oh, we're talking. So we're talking about just loop A's knowns right now, not the other one. Which I'm gonna put a text box in there that says B. Anyway. So, oh no, what happened? It went away. Wait, really? How do you redo? Where's the redo at? Redo. Whatever. That did not go according to plan. Scrap this from the video. Knowns and unknowns. Cut the mic. So loop A. So we have theta 2, R2, theta 3-1, R3-1. And this is the K's and the U's, which is theta 3 and R3. Alright. We can agree with that. There's our unknowns for that one. Now we have to do the next one, which is loop B, or loop B. Knowns. So let's start with the first one. So let me go back up a little bit. So we start with R3-1, R4-1, R4, and R1. So does R3-1 change angle, or I guess anything else? Theta 3, and R3-1. I agree. Theta 3-1, R3-1. All right. What about, let's move up to 4-1. So is theta 4-1 and R4-1 known? Well, I can tell you for sure theta or R4-1 is not, right? Because as this thing slides further this way, so like as this pin goes this way, this length is getting longer, right? Yeah, it's not. So we'll go ahead and put that one in the unknown category. So R4-1. I agree. What about theta 4-1? Anybody? You think it's known? Why do you think it's known? I think it should be unknown for the exact same reason that our theta 3 is unknown. So if you look at this right here, so do you see how right now, how this looks? As this thing slides further inward here, right, you can tell that this thing is stretched out to its, well, it's at its maximum length right now. But as this thing moves closer this way, it's going to push up this length 3, right? And make it more horizontal, right? Or, you know, like almost parallel with the ground, right? And what that does is that it pulls this angle and makes it more flat. And it does the same thing with theta 3 here as well. So essentially, as this one pulls in here, it's going to straighten out this whole thing. Yeah. So R41, theta 41. Unknowns. Let's move on to R4 and theta 4. R4, for the same reason for all Revolut links, it is a known because it is from here to here, right? It's just 2 pins. They are pinned there. R4 is known. What about theta 4? Will the angle of this line always be the same as this thing moves and, you know, turns around these points? The answer to that question is no. It will definitely not, because as this thing pulls this way and like straightens out, this angle for R4 will kind of open up or close, right, depending. So we have theta 4, right? And now we have one last one right here, which is R1. What do we do with R1s in general? We like to draw our coordinate system. Kind of going along, well, I didn't really do a good job of that, but we draw our coordinate system that goes right along that axis. And so what that does is that, you guessed it, it removes the angle from the unknowns. And we can, well, okay, once again, I've said this before, it doesn't remove it, it just simplifies it to a point where our equations are easier. I always missay that. So both R1 and theta 1 are scratched off because R1 is just a distance between these two grounds and theta 1 is 0, right? Alright. And every time I do this, I always forget to finish the text box. So, we're going to do it again. Loop B. Okay. We had theta 31, R31, R4, R1, theta 1. And unknowns, we had theta 4, R4, and, oh no, that's not right. It was theta 41, theta 41, R41, and theta 4. Right? I think that's what we came up with, right? So it's this angle, this line, this angle, everything else is good. So we're good. We have our knowns and unknowns, loop A and loop B, right? So now, the third step in our grand design is that we have to get the proper equations and unknowns, right? Does that make sense? The proper equations and unknowns. So, let's do another text box. We need to have, for step 3, equations must equal unknowns. So that means extra must be found. So essentially, extra equations must be found. So our extra equation, do you guys have any ideas how we could come about an extra equation for this picture? Well, once I get up there. So for this picture right here, There's probably a couple ways to do it. Between R1 and 2. That is good. That is actually what that's the other way that I thought to do it. What you could do is, I'm gonna lose my text box, but what you could do is, I'll just use Epic Pen for this one. Actually, no, it doesn't work. Never mind. So what you could do is, you could do theta 2 minus theta 3,1 has to be equal. So if you do theta 2 minus theta 3,1, let me see if that's right. So this is there, and if you subtracted that, would you get? It'd be this part in the middle. It's equal to alpha or something like that. It would have to be theta 3,1 or theta 3,1 minus theta 2 gets you to alpha. I think is equal to alpha or something like that. But there's another one as well. Because essentially right here, this is theta 3,1 and this is theta 2. So if you subtract theta 3,1 from any time this is moving, it'll pull it back to some angle alpha, and you could find it from there, because theta 3,1 is always the same, and we know what theta 3,1 is. So I think that one would work as well. But the one that I was thinking, so look at this part up here, Rosendo. This is the one that they did. So me and you were on the same page. I think you can do it that way. But me and you, what about up here? What about theta 3 and theta 4,1? What do they always have to add up to if you take both of those? They always have to equal 180 degrees. You are right. And frankly, they must be the same angle, right? At all times, essentially. Would you agree with that? Because as this thing pulls up, they both start to even out at the exact same rate. Would you agree with that? They essentially have to be the same. Because as you can see, they both have to follow this line of this slider, right? Which means that their angle must be the same, right? Because they share a line of the slider. Which means that you can eliminate an unknown by saying the following equation. Sorry, we're getting down to the last one here. So theta 3,1 minus theta 3,1, or it's 4,1 for us, sorry. 4,1 minus theta 3 is equal to 0, or 180 degrees, as you said. Which, if you guys simplify that, you would find that theta 4,1 and theta 3 must be the same. And that is simply a property because they are sharing this exact same line of this slider. So as this one moves up and this angle becomes a little bit less sharp, this one must do the exact same. They move and perfectly relate to each other. So that is the third equation that we must, or the next equation we must find. But I think you can do it the way you talked about it, Rosendo. I'm fairly certain you can. So, good eye on that one, for sure. So, right now we have unknowns, that's 2. And we have 3 right here is 5. From these 2 vector loops, we got 2 equations, and then 1 right here is the 5th one. So we now have an equal number of equations and unknowns, right? So perfect. That means you can move on to the last step, which the last step essentially is start solving the question, right? So step 4, derivatives. So first and second derivatives of the position equations, which are the scalar. So I'm going to go ahead and make this one really big. So I'm going to start with x prime, so x prime of this equation right here. So if you take the derivative of this one, so you would have, so remember this is cosines and sines, right? So I'll just write that out actually. I'll do x is equal to R2 cosine. I really wish I had, can I put T2 for theta 2? I feel like writing out thetas is going to make this like really long, so I'm going to do that. R3 cosine T3 minus R31 cosine T31. Y, same thing. R2 sine T2 plus R3 sine T3 minus R31 sine T31. Right? Make sure I did that right. Yep, it appears so. So that is the first equation. I'm only going to do one set of derivatives because we don't really need to do both of them because it's the same process, right? We're only going to do the first one. So this is x and y. This is the position equation. So now we have x prime and y prime. So this is the first derivative of the position equation. So if we take the first derivative of this first one right here, we get minus R2 sine T2 minus, because we're going to change the sign. Remember, R3 now. So remember, we have to go back to our variables. R3 is an unknown, and so is theta 3. So therefore, we get out of this one, we get or F3. So F3 cosine T3. Yeah, I'm actually gonna change this one back. I'm gonna do a plus here and put this in parentheses. Minus R3 sine T3. Right? Because remember, we had to take the derivative since they're both, oh, there's an H3 here. Someone was about to tell me. So why we do F is because if you take a derivative of a vector length, so essentially it's a substitution. So the derivative of a vector length that is changing is it's the change of that vector length with respect to the input, which is theta 2. So they would be dr3 over d theta 2, and dr3 over d theta 2 is replaced as f3. Instead of writing all that in there, we just put f3. And that is the kinematic coefficient. That is what these things are. F3 and H3s and all types of F's and H's are kinematic coefficients. Essentially, they're placeholders for the change in the position or the change in velocity or the change in acceleration of that point. Yeah, that's what they are essentially. But so this made sense to you though, the derivative? That was good? All good there? Okay. Alright, and then minus R31 and cosine theta 31. So both of these are known if I recall. So you treat them sort of the exact same as before. Wait, did I do this one? Oh, we named it differently. Okay. Yeah, I completely forgot. Yeah, we named them differently. So I was trying to like look through and like see if we did that right, but it completely screws up. So remember, R31 and cosine theta 31 are both known quantities, right? Do you guys agree with that? They are. which means that since this angle never changes, so if we go back up here, right? Since this angle never changes and this length never changes, the derivative of a known quantity is what? So it goes away. It's 0. So I'm not going to put a 0 there because I feel like that would be more confusing, but there is a 0 here for this part right here, the R31 part. Because this angle right here, so essentially if you do, so I know people are like, well, wait a minute, we don't know what theta 31 is. But it doesn't really matter if we don't know it, because we don't know the actual number. It doesn't matter because we can measure it, and if it never changes after we measure it, it just means that cosine of an angle is some number. You know what I mean? It's a number. Therefore, the derivative of just a number multiplied by just a number is 0. So that's why that happens. So R2. Now we got to do this one. R2 cosine T2 plus F3. Yeah, let's do that. F3 sine T3 minus, or plus, sorry, plus R3 H3 cosine T3. Make sure I'm doing this right though, because I am going through kind of fast. So essentially the first derivative, once again, you take the derivative of R3 because it is a variable, and you get F3. And you leave the other one alone. And then this is the product rule. And then you do the derivative of the sine part of it, right? The sine part of it, and leave the other one alone. So you get the H3, you left this alone, and you get a cosine because the derivative of sine is cosine. And then once again, same thing as last time, this last part goes away because it is a known quantity. X double prime and Y. And nope, wrong key. X double prime. So the next derivative, which is the second one in our chain, we must do the exact same thing. We do R2, so minus R2 cosine T2 plus, now once again we've reached another point where we have some different variables in here that are both unknown. So you have to do the same thing here. We do F3 prime, so it's minus actually, so it's minus F3 prime sine T3. Oh, wait a minute, no, I did that wrong. It's just F3 prime cosine T3. Then you take the derivative of the other one. Yeah, my fault. Minus F3 H3 sine T3. So we've only done this one right now. Just so everybody's aware, we've only done this one. So we took the derivative once again of F3, we got F3 prime and left cosine the same. Then on the next one we have F3, you left this the same, and you took the derivative of this, which gets you negative sine, which is why the sign changed, and you pulled an H3 out. So all good there. Let me go ahead and shut that one. And then we have to do the next one, which is minus. So you take the derivative of R3, which once again is changing. So this is the triple product rule one that I was mentioning the other day. So this one is F3 H3 sine T3 plus H3, oh, it's R3. I'm trying to keep it in order for you guys. R3 H3 prime sine T3 yeah, so I'm gonna make sure I'm doing this right. So F3 H3 sine R3 sine H3 prime, sure. Yeah, this is really long and painful. Let me move this down. Plus the last one, which is R3 H3 cosine. Oh, it's H3 squared. Aha! I about forgot it again. cosine of t2 or t3. That is quite a lot. And now basically the other one exists the exact same, just in the opposite. So I'm going to write it out really fast so everyone can see. Minus R2 sine 2 plus F3 prime, and I skipped out of it, T2, T3, plus F3 oh, it's a negative sign because we swapped from cosine to sine. Minus R3 H3 squared sine T3 0 equals 0. So once again, the thing that you're going to be tested on is specifically your ability to do this part and your ability to navigate these knowns and unknowns. So basically your exam is going to be as follows. I'm going to give you a vector loop such as this, right? Or something, something of the like. I'm not going to tell you what is unknown and known. You will have to figure that out yourself. And once you figure it out, you will have to then determine whether or not you have the proper knowns and unknowns to solve the question. If you do not have the right equations, or if you do not have the right number of equations, you will have to find one yourself. And if you do not do that, there will be a penalty, obviously, because that's part of the question. But I forgot to take the derivatives of the second of the other equation, which is this right here. So if you take the derivative of this down here, theta 41 minus theta 3 equals 0, you get h41 minus h3 equals 0, and then you get h41 prime minus h3 prime equals 0. And then you will have to return me all of this. This is what I'm looking for. This will be the main part of your exam is doing this. The vector loop part, creating it, that's not as concerning. All right. Well, glad that just happened. Anyway, I'm not rewriting that. So before you leave, though, I'm going to take attendance, but have a good day afterward.